The moon is shrinking, not as a metaphor, not in some distant theoretical future. It is physically getting smaller right now, and it is cracking apart because of it. If that sounds like science fiction, it is not. The data comes straight from NASA, and what it reveals changes pretty much everything we thought we knew about our closest neighbor in space. Here is how it works. The moon formed about 4.5 billion years ago. Since then, it has been slowly losing its internal heat. Think of it like a grape slowly turning into a raisin. Except in this case, we are talking about a rocky body roughly 2,159 miles across. As the interior cools and contracts, the outer shell, the crust, has nowhere to go. It cannot compress neatly inward. Instead, it buckles and folds. The result is what geologists call lobat scarps, which are essentially cliffs produced by the compression of the lunar crust. Some of these scarps are only a few feet tall. Others exceed 300 feet. The Lunar Reconnaissance Orbiter, which NASA has been operating in lunar orbit for over 15 years, photographed hundreds of these formations spread across the entire surface of the moon. The images were some of the clearest evidence yet that the moon is not a dead, static world. It is alive, in its own slow and grinding way. The total amount of shrinkage since the moon formed is estimated at roughly 150 feet in circumference. That might sound insignificant for a body this size, but consider that this process is still happening. The moon is still contracting, the cracks are still forming, and some of those cracks produce moonquakes. In 2024, a study published in the Planetary Science Journal brought this issue into sharp focus. Researchers analyzed seismic data collected during the Apollo missions and traced a magnitude 5.2 moonquake from 1973 back to a specific lobate scarp near the lunar South Pole. Magnitude 5.2. That is not a minor tremor. That is the kind of shaking that rattles buildings on Earth. And here is where this stops being just a fascinating geology story and starts being a very practical problem. The lunar South Pole is exactly where NASA plans to land astronauts as part of the Artemis program. It is where permanently shadowed craters hold deposits of water ice. It is the most strategically important destination in space exploration right now, and it sits on ground that can produce magnitude 5 earthquakes caused by the moon tearing itself apart. Think about what that means for a lunar base. You need stable foundations. You need equipment that stays put. You need surfaces that astronauts can walk, drive, and work on safely. A magnitude 5 moonquake in a vacuum does not carry seismic waves the same way an earthquake does on Earth, but it can trigger landslides in craters. It can displace regolith, which is the layer of fine rocky powder that covers the lunar surface. That regolith is worth pausing on for a moment. Unlike beach sand, which has been smoothed by water and wind over millions of years, lunar regolith is made of microscopic shards of rock shattered by billions of years of meteorite impacts. It is razor-sharp, electrostatically charged, and it sticks to everything. A regolith avalanche triggered by a moonquake is a genuine hazard for anyone on the surface. What makes this discovery even more significant is what it tells us about how we think of rocky bodies in space. For decades, the assumption was that worlds without plate tectonics and without active volcanism were essentially geologically dead. The moon fit that description perfectly, or so we thought. We now know that is wrong. The moon still has a partially warm interior. It still releases energy, it still moves. And it is not alone in this. Mercury went through a similar process of thermal contraction, but on a far larger scale. The Messenger spacecraft mapped scarps on Mercury that dwarf anything we see on the moon, which makes sense because Mercury is smaller and lost its internal heat faster. The difference is that Mercury is not somewhere we are planning to send astronauts anytime soon. The moon is. So how long will this shrinking continue? The honest answer is that we do not know precisely. The moon has been cooling for billions of years and will continue doing so for billions more. The process is far too slow to observe directly in any human lifetime. What we can do is monitor it. The Apollo missions left seismometers on the lunar surface that operated between 1969 and 1977. In that 8-year window, they recorded over 12,000 seismic events. 12,000. The moon is not a quiet place. It rumbles, it shakes, it creaks under the stress of its own cooling core. NASA and other space agencies are now developing next-generation seismometers for future lunar missions, including instruments that would be part of permanent infrastructure on the moon. The goal is to build a detailed seismic map before humans commit to long-duration stays on the surface. And long-duration stays are exactly what the plans call for. The vision for lunar exploration in the coming decades is not just land and come home. It is establish a sustained presence, build structures, create the infrastructure that makes the moon a stepping stone to Mars. All of that requires understanding seismic risk at a level we have never needed before. There is also a human dimension here that does not get enough attention. Astronauts on extended missions already deal with isolation, radiation exposure, the physical stress of low gravity, and the psychological weight of being far from home. Adding the reality of living on a surface that can shake without warning raises new questions for mission planners and the teams responsible for crew mental health. But to be absolutely clear about one thing, the moon shrinking is not an existential threat. The moon is not going to fall apart. It is not going to disappear from our sky. Losing 150 feet of circumference over 4.5 billion years is, in cosmic terms, a rounding error. The moon will be with us for an almost incomprehensible stretch of time. What is changing is our relationship with it. We are moving from being occasional visitors to potentially becoming long-term inhabitants. And that requires knowing the ground under your feet. The shrinking moon is also a reminder of something easy to forget. The universe is not a painting. It is not a static backdrop. Every planet, every moon, every star is in some phase of change. Some changes take billions of years. Some happen in seconds. The moon quietly contracting over geological time is just one more chapter in the endless story of transformation that defines everything we can see in the night sky. For thousands of years, the moon guided sailors across oceans, set the rhythm of calendars, inspired poets and scientists and dreamers. And even after all of that, even after Apollo, even after everything we have mapped and measured, it still has surprises for us. A world that cracks, a surface that quakes, a destination that is changing beneath our feet before we even set up camp. We are going back to the moon, and now we know it will not be entirely still when we get there.